in like 24 hours. Follow up with me, because chances are through all the mess of emails, yours somehow slipped through the cracks, which I totally hate. I don't like to do that, but it does happen. I apologize. So if you have a question on an email and it's pressing, just email me again. But if you haven't heard back from me in like 24 hours, that's not normal. So just shoot me another email and I'm happy to chat. Okay, so we had some assignments due last night. I hope they went well for everybody. Mastering chemistry can occasionally give people headaches. And I don't know if I've announced this. I know we're still waiting on people to join, but hey, the early birds get some extra worms for being on here early. It may have told you on the steps for logging on that if you use Chrome as your browser or even Firefox, that's the best way to go about it. Safari tends to give people fits. Mastering just isn't super compatible with Safari. So if you ever run into an issue with Mastering, check your browser. And I use Chrome personally for everything, and I've never had issues with it. So, or if you do, just screenshot the problem, like maybe you're typing in an answer or something, is getting weird on you. You can screenshot it and send it to me and I can look at it with you. Also, people have been questioning, hey, I got this grade on my mastering assignment. Here's what the grade shows me in the mastering chemistry, and it's different on Blackboard. Why is that? And sometimes it just takes a minute to get the actual correct grade onto Blackboard. Usually it's correct in my grade book. So if I check, like say you get a 5 out of 5, but for some reason on your Blackboard grade book, it shows a different grade. Give it like 24 hours and it should update. But if you're experiencing that issue for longer than that, let me know. Our Pearson representative, I've been meaning to share this link as well. There's like people you can reach out to at certain times of the day if you run into issues with mastering chemistry. They have like virtual office hours and stuff. So I need to send that. My grades were different, but update later on the day. Okay, good. So yeah, usually if you just kind of wait around and check it again after a day or so, it should be correct. But if it's not, always feel free to reach out to me. I may not have the answer, but I can connect you to somebody who does, because I'm not a Pearson person. I use it for my course, and I know how to make the assignments and everything, but I don't know. I'm not like, a Pearson engineer. So, okay. Well, it is 10:50, so we are gonna get started with a few announcements. First announcement, if we have a tornado siren or something crazy go off during this lecture, we will not continue class in our closets. I'll just record the rest of it and let you watch it, okay? Your safety is more important. So I've got people that are texting me like, are y'all gonna be okay? We're very worried. Do you get multiple tries for the homework? Great question. You get one attempt for the homework. So these first couple assignments, I think at least on the primer, I gave you multiple attempts. But on the homework, okay, yes and no, actually. You get one attempt for the whole thing, but you do get multiple attempts for questions. Now, it will start to count off a small percentage of points for incorrect answers, but you don't just get like one try, like if you input one answer for a question and it's wrong, you do get to try again. It's just you do start to lose points for incorrect answers. So now it's not a large percentage of points. It calculates it in its own special way, but you can try again on any particular question. And I think you get up to 6 attempts per question before it just says, hey, you probably don't know this. And it gives you no points for that question. So you do get multiple attempts per question, but not for the entire homework. Like you complete the whole thing and then you get a whole nother attempt. No. So I hope that answers your question. But moving on, if you ever read a question, you're like, I don't even know how to begin this. So before you even try to put an answer in, I encourage you to try at least once. But if you really are stuck on it, just shoot me a screenshot, because with these assignments, they're not timed. So you can leave and go do something else. I think I've explained this maybe once, but you can leave, go do something else if you have another class or whatever to jump onto, and then you can come back. So they're not timed on mastering the way like our quizzes and our exams are timed on Blackboard. Okay. For those, you have to sit down and get it done in one go. But the time zone on my homework was wrong. So it didn't give me the credit. Late. Okay, that's very interesting. Thank you for letting me know that, because I checked on the time zone or I had our Pearson rep check on that, because actually the previous semester we were set to a different time zone. So when I was telling everybody it was due at midnight, it was shutting off at 11. It was like East Coast time zone. So I'm going to make a note of that right now. Check on time zone, because I thought it was set to the correct one, but I will have her double check. Sorry, hold on. Thank you for letting me know. All right. Any other questions or things with mastering? Okay. You probably saw my email. I slipped up this morning. I did not turn that quiz on at 8 a.m. So sorry, but I extended the deadline. So it's not due at 5 p.m. anymore. It's due at the end of the day. So you actually have even more time than you would have previously. But it is available now. You have 20 minutes to complete it. It's 5 multiple choice questions, open note, open book. You'll need a calculator. I would have a piece of scratch paper. You do have to sign an academic integrity statement at the beginning. And if you don't sign that, if you choose not to, or whatever, if you forget, you get 0 credit for that quiz. So please make sure you sign that with your name and your student ID, okay? It's 5 points though. And I don't have makeup quizzes. So if you miss the due date and you forget about it, it is what it is. Very sorry. Okay, then still, I'm going to always encourage you to check out the discussion boards. I'm going to post a new discussion board probably today, probably not tomorrow, because we are doing birthday festivities tomorrow at my house if we don't have a hurricane in our city. But I will post another discussion board soon. And if you have responded to the discussion board and I have not got back to you yet, I will respond by the end of the week. And then I know I mentioned this again. I have not started. Today, I plan to put 2 or 3 videos up, short videos. I'll link them to Blackboard on the dry lab, like how to work particular problems on the dry lab. So let's say you group A people, you finished your wet lab. Now you want to go ahead and get started on the dry lab. I'm going to start posting some videos. And you group B people, by the end of today, we will have covered all of the material to complete that dry lab. So I think these videos will now become really applicable for you to start that assignment and do that. Okay. Last reminder is that I still am getting emails about this, so that's why I'm clarifying. I feel like I'm beating a dead horse a little bit, but Group A people, your wet lab assignment is due no matter what Blackboard says about when it's due. It should say 11:59 p.m. Friday. Group B people, the actual deadline is set to September 4th, okay, for the wet lab. That's detecting signs of a chemical change. You have till next Friday, because you're not doing it until next week, to complete the wet lab. And the dry lab for all groups A and B is not due till September 4th, Friday at midnight. Okay. If you have any questions on when those things are due, let me know, but hopefully that clarifies. That's all my announcements. So let's get into lecture. We're going to pick up where we left off. So I'm going to share my screen. Okay. Okay. Here we are. I'm going to back up just a little bit because we were doing some simple conversions. Okay. Here's actually where we left off. We skipped over a few of these. So I'm going to pick one off of this slide right here. We'll work it, and then we'll actually also work another one, and then we're going to move on to some temperature stuff. So any problems that I don't work, I encourage you to try as extra practice. That's a really good thing to do. Always reminder, have your pencil and paper and calculator out and do these with us. Don't just watch me do them. It's to your benefit to do them ahead of me or with me on lecture. So Tuesday, we talked about units, why they're important. Put a unit on every number. We talked about prefixes. So that's the milli, micro, nano, kilo, and then the base units that those can be prefixes for. So the gram is the base unit for mass. The liter was the base unit we talked about for volume. And the meter is the base unit for distance. Okay, so the gram, the meter, the liter, and you can put a prefix in front of each of those and it changes the size or the quantity of that property. So let's look at this one right here. We have 374 UL, microliters, okay? When you see that, you should immediately think micro, okay? Because that U with the tel on the front is the prefix for micro. So microliters, so we're talking about volume here. We want to know how many milliliters is this, okay? ml. So we need a relationship. We need what we called a conversion factor that relates microliters to milliliters, okay? Now, if you don't have one that does that directly for you, we could scroll up to the table on volume that had all those relationships and probably find one there. But if you've memorized these like I've asked you to, we do have relationships between micro and the base unit, liters. We know how many microliters are in a liter, and we should know how many milliliters are in a liter. So we can actually do this in 2 steps, or we can come up with a new conversion factor directly from micro to milli. I'm going to do this in 2 steps. I'm going to relate microliter to liter and then liter to milliliter. So the first conversion factor we'll need. We should know, if you look at previous slides in this lecture, that there is, I'm going to use scientific notation. There's 1,000,000 10 to the 6 microliters in 1 liter, okay? Now remember, you can write the conversion factor 2 ways. You could say 10 to the 6 UL on top and 1 liter on bottom, or you can write 1 liter on top, and 1,000,000 microliters on the bottom. And so we'll pick which conversion factor we need in a minute. The second relationship we will need, hold on, I want to look at the chat. People are typing. Are you screen sharing? I'm not seeing anything. I am screen sharing. Can people see? So what I would say is, if you're having trouble seeing me, hop off the Zoom and log back on. Okay, and make sure, I don't know, click your video, make sure that's on, maybe, but seems that everyone can see me. Okay, good. All right, conversion factor number 2 is that there is 1,000, or you could write 10 to the 3 milliliters in 1 liter. Okay, so you can write 10 to the 3 as well. All right, so we're going to start with the number given. Always start with the number given, 374 microliters. So I'm going to write that down here, 374 microliters. We're trying to convert to milliliters. This is going to be a 2-step process. So I like to draw a line and put it over a 1 so that I see microliters. That unit is on the top starting out. Now we're going to use this first conversion factor, and we need to pick either the one over here on the left or the one on the right, so that microliters cancel. And the one we need is this one right here, because microliters is on the bottom. So that will allow us to cancel micro. So I'm going to write that one in, 10 to the 6th microliters over 1 liter. Now, I like to do this as I go. I have that unit on top and bottom, so it cancels. So now I have successfully converted to liters. I have one more step to get it to milliliters. So I'm going to use my second conversion factor or relationship. I actually haven't written it as a factor yet. If we go ahead and just write it straight in, I want liters on the bottom this time. So I'm going to put 1 liter on the bottom, and the relationship is right here. For every 1 liter, we get 1,000 or 10 to the power 3 milliliters. Okay, if you write 1,000, that's okay too. Now we see we have the units of liters on top once and on bottom once, so they cancel. And now all the units have canceled except for milliliters, which is what we wanted in our answer. So we're there. All we have to do is the math now. Remember, anything on the top, any numbers above the lines, you multiply. Any numbers below the lines, you divide. So you do 374 divided by 1,000,000 times 1,000. And what you should get is 0.374 mLs. Okay. Questions there? Anybody get something different? If it was merely like, no, I didn't get anything different. That's what I got. All right. Again, you can do this in 1 step. If you figured out how to do that, all you need to do is write a relationship, a special relationship directly from microliters to milliliters. Okay. If you look at that, there's actually 10 to the 3, 1,000 microliters in 1 ml. Okay. But I'm not going to take the time to actually work that out. So moving on. I would say try this one on your own. You can try this one up here on your own. Let's look at this one right here. It's kind of a word problem. At least it's in sentence form. So let's read it and try it. It says you must transfer 0.000067 liters. So that's a very small amount of liters of a morphine solution into a plastic tube. How many microliters is this? All right. So we're going to start with the number given. Well, first we need a relationship that relates liters to microliters. And if you look at the slides prior, and we actually wrote it right here. There it is from our previous question. 1,000,000 microliters in 1 liter. So I'm just going to write that up here. 10 to the 6th microliters equals 1 liter. So that's what we're going to use. Start with the number given, which was the 0.000067. If you don't want to write all those zeros, you could write it in scientific notation. 2, 3, 4, 5. So it'd be 6.7 times 10 to the negative 5 liters. And that's over 1. So I have units of liters on top. Now let's convert directly to micro. So I want liters to cancel, and I want to end up with micro because that's what the question's asking for. How many microliters? So I'm going to put 1 liter on bottom. I'm using this relationship now. I'm going to put 1 liter on the bottom, and I'm going to put 10 to the 6th microliters on top. And liters now cancel because I have that unit top and bottom. And so this was just a one-step conversion problem. So you have the 6.7 times 10 to the power of negative 5 times 10 to the power of 6. And you should get, I believe, 67 microliters. Is that what you got? Okay. All right. Last one we're going to do is this miles to kilometers. And then we'll actually move on into new material for the lecture today. Grab a drink. So read the problem really quick. 26.2 miles. Anybody ever run a marathon before? Any marathon runners in the class? You're like, yes, in all my spare time I run. Some people do. That is a long way to run. All right, 26.2 miles, the distance of a marathon. How many kilometers are in a marathon? So we need a relationship from what to what? What are the two units we're working with here?
Miles to meters.
Close. You're almost there. Miles to
kilometers.
Kilometers. There you go. So we need a relationship that relates miles and kilometers. Now, I hope that this doesn't make your head spin. We should have it on the table of distances way up here because I don't have that memorized. And I would not expect you to have that memorized. So that's math. Okay, here it is. On this table, do we have a relation between miles and kilometers? And we do. 1 mile is this many kilometers. Okay. Or you could use this one. 1 kilometer is this many miles. Either one works, just so you know. I'm going to pick the one we circled first, right here. 1 mile equals 1.609 kilometers. All right, close your eyes because I'm about to scroll. All right, right here. 1 mile equals 1.609 km. All right, so start with the number given, 26.2 miles, 26.2 miles. Now, I want to do a little concept check here. I think these are very healthy to learn how to do when you're working problems like this in this class. Should your answer be bigger or smaller than 26.2? Like, are you going to have, is a mile more kilometers or is it more miles? Essentially, you got to know that, you got to think, okay, which unit is bigger, a mile or a kilometer? So if you look at the relationship, 1 mile is almost 2 kilometers. So which one's bigger, a mile or a kilometer? The kilometer, okay. Or sorry, the mile is bigger, kilometer is smaller. So we're going to have an answer that's larger than 26.2. It's going to take more kilometers to equal this many miles, if that makes sense. So I like to make sure if I get a number that's smaller than 26.2, I would be like, okay, I know I did something wrong because I know my answer should be larger number. So we're going to use this relationship. We want miles to cancel. So I'm going to write miles on the bottom and 1.609 kilometers on top. Now this is just a math problem. What did y'all get? Somebody's done it.
$42.1558.
AM. All right. Anybody get something different? 42. Okay. So You could round here if you wanted. You could say 42 point, I would say 16, okay? Or if you said 42.2, you would not be incorrect. There we go. Questions? All right, and then I encourage you to do the milliliters to gallons as well. You'll have to go up to the volume table and you could get, let me just set this one up for you so that you get the right relationships, because I think it's probably going to take more than one step. Here's my guess. My guess is that we're going to have to know, okay, how many milliliters is in a liter? And then two, I bet you can find a direct relationship for how many liters are in a gallon. I bet it's a two-step process. So I would encourage you to try that one, attempt that one on your own. I don't have a plan right now. What do you want us to round to? Hopefully I answered that to you. Just give me one or at least one decimal, two preferably on answers. With this, if you have any questions, I don't have plans to make videos about like, here's the answer for these. So if you ever have a question on one of these, just shoot me an email and I'm happy to double check your work. If you decide to work these, which I encourage you to. This was a slide I think I mentioned I wanted you to try to fill out. I like to just recap what you learned because sometimes it's a lot of information. I want you to know how to summarize the important points. So I'm just going to fill this in real quick before you move on to new stuff. Numbers without units, hopefully you got that, are meaningless. So we talked about units and why they're important. Be able to give me a reason or two for why units are important. We talked about how they're a reference point, okay? We talked about how the reason they're important is because numbers don't mean anything. There's multiple ways you could interpret a number until you know the unit. We write how to write and manipulate numbers in scientific notation. And then we introduce prefixes and their relationship to the, wait, what was that one? Hopefully I wasn't thinking something different. Oh, prefixes, yes. And to the base unit. Okay, so that was the summary of what we went over Tuesday. All right, now let's get into some new stuff. Questions before we jump in? So here's what we're about to go over today. In our remainder of time, we're going to talk about temperature conversions. You're going to have to learn to convert between Celsius, Fahrenheit, and Kelvin. And then we're going to talk about specific heat and how to work those problems. And then we're going to talk about density as well. So temperature. We have on this slide 3 temperature scales. Fahrenheit scale, which we communicate Fahrenheit temperatures the most, just in our English language. We have Celsius, which is like the metric unit for science and research. And then we have Kelvin, which is remember, that's the international unit, okay? But all 3 of these scales are important. I'm going to point a few things out on this picture. If you notice, we have a temperature for where water freezes on all of these, and we also have where water boils. So I want to look at the difference on each of these 3 scales. For Fahrenheit, the difference is 32 and 212, okay? And if you take the difference there, it's a difference of 180. Okay, 180 degrees Fahrenheit. Let's look at it for Celsius, 0 and 100. Okay, so that one's easy. The difference is 100. And then let's look at it for Kelvin, 273.15, and that 0.15 is important. Don't leave the decimals off there when you're doing things with conversions with Kelvin. So 273.15 and then 373.15. So the difference here is also 100. The reason I wanted to point this out is the unit for Celsius and the unit for Kelvin are the same size. So they're same size unit, meaning if I increase 1 Celsius on the Kelvin scale, I increase 1 Kelvin. But it's different for Fahrenheit, okay? We moved 100 degrees on the Celsius and the Kelvin scale, but we had to move 180 degrees on the Fahrenheit scale. So units of Fahrenheit are smaller. Okay. And then lastly, I want to point this out. If I zoom in you'll notice these little degree symbols for Fahrenheit and Celsius, but you don't have that for Kelvin. So it's actually inappropriate to say a degree Kelvin. You just say a Kelvin, okay? So don't ever write, it was a degree Kelvin, just write the Kelvin, okay? But it is degree Fahrenheit and degree Celsius, okay? So with that, moving on, let's scroll down to this next. We're gonna write out a few equations. I want you to memorize the two that we're gonna write out. You do not have to memorize the ones that are already typed for us. So we're gonna look really quick at how to convert from Celsius to a Kelvin temperature, and then vice versa from Celsius or from Kelvin to Celsius. And then we're going to talk through these equations down here, which are conversions between Fahrenheit and Celsius, and they look a little more complicated, and they are. Now, because of what we just talked about on the previous slide, how the units of Kelvin and Celsius are the same size, it's a simple addition and subtraction problem to convert from Celsius and Kelvin, okay? If you're at 0 degrees Celsius, you just add 273.15 to get the Kelvin temperature, because the difference is 273.15. So if I have a Celsius temperature, so if I have degree Celsius, I don't know what my temperature is, but this is where I would plug it in. If it's 10 degrees Celsius, if it's negative 20, if it's 50 degrees Celsius, you plug it in right here, and then you would add 273.15. And then you would get the temperature in Kelvin. Know this, you are going to use this so much this semester, I can't even tell you how much you're going to use it. Vice versa, if I have the temperature in Kelvin, what am I going to do to get the temperature in Celsius? It's the opposite operation. So I have my Kelvin temperature, I'd plug that number in right here. I don't know what it is, but it would be something with units of Kelvin. And then I'm going to subtract 273.15. And I will get the temperature in Celsius, okay? So these you need to memorize. How to go back and forth from here to here, okay? And you just plug it in where I wrote either K or C, depending on if you're starting out in the Celsius or the Kelvin scale. Now let's talk through these other conversions right here, these equations. If I have a Celsius temperature, and I need to get the temperature in Fahrenheit, the equation on the left is what I use. So here, if we have degree Celsius and need degree Fahrenheit, this is the one you use, okay? If you have Fahrenheit and you need to get it in Celsius, you'll use the one on the right. Now let's look at this. It says 9 degrees Fahrenheit, and these are just units that we've added to the numbers, over 5 degrees Celsius, and we're going to multiply that by our temperature in Celsius. Now, where did the 9 over 5 come from? Well, I'll show you exactly where it came from. Let me zoom in over here. We said a movement of 180 degrees Fahrenheit is equal to a movement of 100 degrees Celsius. So if we make that a fraction, 180, and I'm putting the Fahrenheit on top because that's how it is in our equation down here. Let's simplify this. If we simplify it, we can take off a 0 on both. So now we have 18 over 10. Divide the top and the bottom by 2, and you get 9/5. Okay, so we just took that and made it a fraction in simplified form. Okay, that's where the 9/5 comes from. Now, one thing that is confusing to people with these equations that I'm going to point out is you have multiple operations you're doing. You're multiplying and you're adding here. And on the other side, you're multiplying and you're subtracting. It is very, very important. Now, you will have access to these from your notes, okay, on an exam. And sometimes I have a little equation sheet that I'll put like these equations on, especially for exam 1. So you'll have these, but don't let that mess you up on how you do these operations. First thing to answer, where am I plugging in my Celsius temperature? I see 2 degrees Celsius symbols. You plug your temperature. If you have a temperature in Celsius and you're trying to convert to Fahrenheit, here's where you plug it in. This degree Celsius is just the unit for that number 5. So you don't plug your temperature in twice. You just plug it in on the one I've boxed in, okay? Okay, so don't get confused by that. I've seen people mess up because they'll plug it in, the one I boxed in, and they'll plug it in here. and then that throws your whole answer off. So just plug it in one time right there where we don't have any numbers associated. That's your temperature. Then you're going to multiply by 9/5. Notice how the Celsius units cancel, okay? And that's supposed to happen so that we get Fahrenheit. And then once you've done that multiplication, you add 32 to your value, and you get the temperature in Fahrenheit, okay? All right, let's look at the other one. Any questions on that? Now, this other one was if we have degree Fahrenheit temp and we need it in degrees Celsius. So look at this equation. Remember, if something's in parentheses, you do that first. And I forgot to mention that over here, but you're going to plug in your temperature and multiply it by the fraction first. Well, over here, where do we plug in our Fahrenheit temperature? We plug it in right here. You don't plug it in everywhere there's an F. You plug it in right here where there's no number. Okay, that's where you plug in your Fahrenheit temperature. Sometimes it cuts me off at the very edge. Okay, and then you subtract 32. Okay, these other letters are just the units associated with their numbers. Okay, so you plug it in, you subtract off 32, and then you multiply it. Notice it's the reciprocal fraction. Here it's 5/9, and over here on the left it was 9/5. That's because once you do this subtraction right here, you have degree Fahrenheit, and then that will cancel with the Fahrenheit on the bottom. The units will cancel. So your Fahrenheit unit should cancel, and you should be left with degrees Celsius.
Okay, you said do everything in the parentheses first.
Yes, always. So over here, if you're converting from Celsius to Fahrenheit, you're going to multiply by 9/5 first. Then you're going to add 32. Over here, you subtract 32. You do the opposite. You subtract 32, okay, and then you multiply by 5/9. So you do this first, and then multiply. Do whatever's in the parentheses first. It's the order of operations. Have y'all ever heard the, well, it's a saying, but if you take the first letter from each word in this saying, it makes an acronym and it tells you the order of operation. Please excuse my dear Aunt Sally. If you take the letters there, it tells you, and the P, please, stands for parentheses. Excuse would stand for, oh, I forget, but that is, anyways, you always do things in parentheses first. Okay, let's actually put this into practice now. So we have a problem here. Body temperature is roughly 98.6 degrees Fahrenheit. What is body temperature in Celsius and Kelvin? So we have a temperature in Fahrenheit. The first thing we're going to do is convert to Celsius. You can never go directly from Fahrenheit to Kelvin. In fact, I'm going to write that. You can never directly convert from Fahrenheit, degree Fahrenheit to Kelvin. You always have to go through Celsius first, okay? So let's take our Fahrenheit temperature. Which equation do we need? If we're gonna go from Fahrenheit to Celsius, this one right here says if we have Fahrenheit and we need Celsius, which is the direction we're headed. So we're gonna use this equation on the right. So I'm gonna write it out. I'll get my temperature in degrees Celsius once I do this operation. All right, here's where I'm going to plug my temperature in, 98.6 degrees Fahrenheit, and I'm going to subtract 32 degrees Fahrenheit. And this was my temperature. So 98.6 minus 30 would be 68.6, so we should have 66. Okay, is that what y'all got? Degree Fahrenheit. Now we're going to multiply this by our fraction, 5/9, 5 divided by 9. So I think if y'all want to go ahead and do that and type what you get in the chat, it's great. I'm just going to say 5 divided by 9 is 0.55555. So I'll just say times 0.556. And that is, I don't want to leave off units. I'm getting a little crammed in here. So that's degree Celsius over degree Fahrenheit. And we multiply it like that. This decimal, I just took this fraction and turned it into a decimal. Okay. So then times 66.6. And I got 37 degrees Celsius. Okay, so that's half the problem. We did this first part, now we got to get it in Kelvin as well. So let's do that second part. And remember, whenever we have a Celsius temperature and we want Kelvin, we're going to use the one I boxed in up here. We're going to add 273. Don't forget the 0.15. So we're going to say plus 273.15. You get 310.15. And remember, it's not degree Kelvin, it's just Kelvin. So I'm going to, this was our first answer. This was our second answer. And we're done. Questions on that? You will have temperature conversion show up somewhere on exam 1. So be confident and comfortable with how to convert between Celsius to Fahrenheit, Fahrenheit to Celsius, and also to Kelvin. All right. Well, if there are no questions, we are going to move on to, so that was temperature. Now we're going to talk about energy. And this is where we're going to get to the term specific heat. So energy, what is energy? Energy is directly dependent on how much caffeine you have every day, right? Just kidding, but kind of not. Energy is the capacity to do work or supply heat. Okay, heat is a form of energy. If you heat something up, you're making, if you heat a substance or some kind of matter up, you're making those molecules move faster and you're giving them more energy. Okay. Now let's look. We have multiple units for energy. I didn't write the book. I'm just telling you the book. Okay. We have joules. This is the SI unit, and we have calories. This is the metric unit. So calorie is probably what you're a little more familiar with. Research and medicine and things like that tend to use calorie more. And then SI, some research uses joules as well, especially for publications and things like that. Okay, we have a relationship. Because there's 2 different units, we need to know how to convert between these. So they have their own relationship. 1 calorie is 4.184 joules, and I would memorize this. Why? You just want to have it quick in your back pocket when you need it. You don't want to have to go find it. The other relationships are actually fairly straightforward. How many calories are in what is a kcal? What does K stand for? Kilo, okay? So kilo increases something by 1,000. So there's 1,000 calories in 1 kcal. And I didn't even make us write anything in here because it's the same for joules. 1,000 joules in a kilojoule. Now, if we're just talking about kilos, look at this relationship as well. The same applies for kilos as it does for right over here. 1 calorie is 4.184 joules. Well, 1 kilocalorie is 4.184 kilojoules. Okay. But the one I would memorize is the one we put a star by. The others you'll know from prefixes and things like that. Okay, so let's fill in this next thing. Now we're going to talk about specific heat. What is specific heat? It's the amount of energy in the form of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Now, you and I actually should appreciate specific heat regarding water and our body content with water? Very, very much. Here's why. If you look at this table, it tells you several different substances. We've got ethanol, we've got some metals here, and we've got water at the bottom. Look at these specific heats. Notice that it gives it to you in both units. It gives it to you in a calorie unit and in a joule unit. Don't worry about the per gram degree Celsius yet. And on this chart, water is the highest. Water has the highest specific heat. What does that mean? Well, when you're talking about these different substances, the higher its specific heat, the more heat or energy it takes to raise the temperature of it. Okay, if you're in your kitchen and you fill up a pot with water and you fill up a pot with ethanol, can you repeat the specific heat definition? Yes, it is the amount of energy in the form of heat required to raise the temperature of 1 gram of a substance by one. It's just typed for you by 1 degree Celsius. That's the definition. But I'm going to give you, like, as far as here's a practical example of how that plays out. If you are in your kitchen, you have a pot of water and you have a pot of ethanol, same amounts. You measured it, equal amounts, and you turn the burners on, full blast. Which one's going to boil first? Which one takes less heat? The one with the lower specific heat. So ethanol. Ethanol will boil way more quickly than water would. Water has a higher specific heat. So what that means is it takes more energy in the form of heat to raise the temperature of water. Now, why is that important? Why do we care about that? Here's a practical kind of health perspective on it. Our bodies are what percentage of water? A large percentage, right? Like 60 to 70% water. I don't know if you've lived in Arkansas your whole life, but we get cold winters, okay? Not extremely cold, relatively cold. And we have hot summers, okay? If our body was 60 to 70% ethanol, our body temperature would change drastically depending on our environmental conditions, okay? But because our body is 60, 70% water, our body temperature stays constant even though our environmental conditions change a lot, all right? So that's one way to appreciate what specific it is. Now, look at these metals: gold, iron, mercury, even sodium is a metal. What do you notice about their specific heats compared to water? They're all a lot lower. And that makes sense. We know that metals heat up. In fact, let me give you a very practical story. One time I learned this lesson the hard way. Growing up in my house, my mom always cooked and baked. We had a set of plastic measuring cups, okay? Plastic, everyone. Plastic does not heat up the way metal does. Well, Joanna Gaines, she's totally wreck shop in the home improvement department. Well, I got a set of metal measuring cups one year for Christmas. I know, metal measuring cups for Christmas. Don't hate me for it, okay? It's what I wanted, okay? And I have melted butter for like cookies or whatever in plastic measuring cups my whole life. And we're just creatures of habit, okay? I'm so used to filling up a measuring cup with butter, popping it in the microwave. I know, I have a doctorate in biochemistry. I know this, but just in the heat of a moment, I filled up a metal measuring cup with butter and I threw it in my microwave for a minute and a half. I don't remember how long it was. And I opened it up and I grabbed that thing and I nearly yelled some words that I would never want my almost 2-year-old daughter to repeat. So don't put metal in the microwave because it has a very low specific heat and it will burn your hand off. All right, moving on. We're actually going to work a problem with this now. If you look at one more thing I want to point out, specific heat. It has multiple units. It does get complex, but on top it's calories or joules, whatever your energy term is. So pay attention to which one you're using. And on bottom it's per gram degree Celsius. Okay, there's an invisible one here. Okay, per gram degree Celsius. But you don't have to write the one in. I just want you to understand that. All right, let's look at this. We have the equation right here for you. How many joules, so it's essentially we're saying how much energy, but we're in units of joules, are required to raise the temperature of 132 grams of ethanol by 10 degrees Celsius. How many joules? So the question is asking for joules, and what we're going to have to do is some algebra. So I'm going to abbreviate specific heat as SH. So let's look at, I'm going to erase my big circle for a second. Let's look at this equation. It's asking, we're not dealing with calories for a moment. So here's our equation, joules over gram degree Celsius. This is how many joules. So we actually need to solve for this part. And
I can't see what you're writing.
I can't see any of the writing. Huh, what changed? What if I write down here? Can you see that?
Your screen sharing is frozen.
Okay, let me stop the screen sharing and try it again. I almost touched my computer. It's not a touch screen. Stop sharing. Share again. Oop. Okay, are we? Oh, I don't have my pencil on. What about?
Good. It's there.
Okay.
Yep.
Thank you, guys. Okay, so we're going to use this equation. We're going to do some algebra. We need to rearrange the equation to get the item we're solving for by itself. Okay, so we're going to do some algebra. We're going to get joules by itself. Right now, joules is hung up over here as part of a fraction. It's the numerator. We want to get it by itself. So we need to move our denominator. Oops, I'm still on eraser. We need to move this denominator. So I'm going to rewrite the equation down here, specific heat equals, I'm just going to abbreviate joules over gram times degrees Celsius. So if I want to isolate joules by itself, what do I need to do? To move my denominator, I'm going to multiply both sides of the equation by this entire denominator, grams times degrees Celsius. Notice I haven't plugged any numbers in yet. It's just less to write. I would wait to plug your numbers. If you have to rearrange like this, now if you're solving for specific heat, you don't have to rearrange it. But if you're solving for something else, like grams or temperature or joules or calories, I would do all your rearranging first before you plug numbers in. So grams times degrees Celsius. Okay, now what happens? We have units on this right side on top and bottom. Okay, we could say this is over 1. So we have gram degrees Celsius here, and on top, remember when you have units on top and bottom, they cancel out. And here's our new equation. Anything that we haven't crossed out is our new equation. So now I'm going to write the new equation down below. Grams times degrees Celsius times the specific heat, we'll plug these numbers in a second, is going to give me joules. And that's what the question is asking for. Now I have joules by itself. Now I can plug my numbers in. Numbers and units. Okay, so let's do that. So here's the mass of ethanol, 132 grams of ethanol, times, and let me point this out. I haven't mentioned this, but when you're plugging in the temperature, what you need to plug in is how much the temperature changed by. Okay, the question says to raise the temperature 10 degrees Celsius. There could be times you read a problem, and in fact on the dry lab, there will be problems you read where it says the initial temperature was 10 degrees, the final temperature was 50 degrees. You don't plug either of those numbers in, you get the difference, how the temperature changed. So you would do 50 minus 10, you'd plug in 40. But here it's communicating what the change in temperature is already. It's just giving you that one number, so that's what we plug in, 10 degrees Celsius. If it told us initially the temperature was 20 degrees, the final temperature was 30 degrees, it would still be a change of 10. We would just have to figure that out first, okay? So it's the change, I'm gonna write that change in temp. That is what you plug in right there. All right, and then lastly, we need the specific heat of what? Of ethanol. Okay, so let's go to our table. Here's ethanol. And which one do we want, 0.59 or 2.5? Sorry, I bet somebody said it in the chat. I'm trying to get the window to come up so I can see my chat. There it is. Would you temp decrease? Abby, I'm going to come back to that question in just a second. Let's finish this real quick. We're in joules here, so we want 2.5. Okay, that's the specific heat we want to plug in. So make sure you're working with the right units when you do this. So it would be 2.5 joules on top. I'm going to draw a line because we have gram times degrees Celsius on bottom. That's all part of the units of specific heat. Now, if it helps you to draw lines in, We've got to cancel units now. The question says how many joules, so we should have no units in our answer except joules. So does gram cancel? Well, I have it on top here and I have it on bottom here, so yes, it does. Does degrees Celsius cancel? I have it on top here and I have it on bottom here, so yes. And then the only thing I'm left with is joules. Now this is a math problem. 132 times 10 times 2.5. What do y'all get? Should be like 2,600 something joules. 3300. Is that what you got? Good. Okay. So that's how you work. That's an example of a specific heat problem. Here's how we can change these up. Instead of solving for joules, or I can ask you to solve for calories, right? And you could work it with calories. Instead of solving for the energy term, I could give you all the information you need and say how much mass, how much does our substance weigh? How many grams are we dealing with? And you could solve for the gram portion. I could say, here's the specific heat of a certain substance, and here's how much energy you apply to it, and here's how much of it you have. You have 70 grams. How much are you going to increase the temperature of it by? Okay, you could solve for the degrees Celsius portion. So I could have you solve for any of these terms, and it's just algebra. You plug in everything you have, and you solve for the missing term that you don't have. Okay, so there's more examples of this on the dry lab, which will have you solve for all the different portions. Questions on that? Okay, now Abby had a question. Would you multiply negative temp if the temp decreased? Well, the answer here is no, and here's why. It's just a change. It doesn't tell you if we're plugging in the change in temperature, the absolute value of a change is always positive. Whether it decreased or increased, it still is a positive type of. We still see that change in a positive sense. So you always are going to plug in a positive temperature. Does that make sense? Yeah. So your temp should always. That's a great question. Your temperature should always be positive because you're changing temperature. That's what I mean. All right. So that's specific heat. We're going to move on to density, and we're going to try to get. We don't have a lot of time left. Oh, we have some. We are going to try to get to some complex conversion problems. So let's talk about density for a little bit. All right, what is density? I've got to get a drink of water. Okay, so density is a property, first off, of any matter. You can measure the density of anything. We know things that are less dense tend to float, and things that are more dense tend to sink, okay, if they're in water or a particular liquid. So mathematically, though, what is the equation for density? Hopefully you've seen this before. It is just mass over volume, okay? Now, we know the base unit for mass is the gram. We actually don't commonly use the base unit for volume, which is the liter. We use milliliter, okay? So that's why units of density are shown right here. It's gram per milliliter. Gram is the base unit for mass. Milliliter is a unit of volume. Now, a little picture illustration here. We have these two cylinders. Pretend that these are like containers that hold a certain amount of gas. And the gas particles, we can happen to see them. They're red. They're flying around in these cylinders. Which cylinder would you say has a higher density? The one on the left or the one on the right? You can unmute yourself if you want to share your answer.
Right.
The one on the right. Thank you, James. Okay. This one has a higher density. Why is that? Let's look at this. Well, what do you know about the volume of these cylinders? They're the same size, right? Same volume, but one has more mass, okay? All of these particles weigh something, and we have more mass because we have more particles. So as you increase mass, you increase density. And we'll actually do another illustration of that later. But things with the same volume that have a higher mass is going to have a higher density. Now, here's just a table. It shows you different substances in different states of matter. So we have some gases, we have some liquids, and we have solids. And if you look at the numbers, the density for these things, I know the units aren't posted, but if you look at the numbers, solids tend to be more dense, and that makes sense to us. Gas particles tend to spread out and have larger volumes, but solids tend to be more dense. There's more mass per unit volume with solids than there is with liquids and gases. And remember that diagram we drew the very first lecture last week, where we drew how the solid particles in a solid state of matter are closer together. Liquid, they're more spread out. Gases, they can fly around anywhere. Okay. All right. So let's look at the only exception here, and you guys are familiar with this, is water. Let me just point this out. Water as a liquid has a density of 1.000, and water in a solid state has a lower density. And y'all are familiar with this. Here's how you're familiar with it. I know it's not a whole lot, but it is slightly different. That's why ice floats. But anybody ever put like a bottle of water or a soda in the freezer and you forget about it? Well, it's got a fixed volume. The container that that liquid is in is fixed. And because it expands, what happens is the molecules expand as it freezes. And so because the density is lowering, and it will often bust, right? Because the volume is fixed, yet the molecules are expanding as they go from liquid to solid. So that's why the density bias is lower. But a few things about density. Density is temperature dependent. And with the whole ice illustration and the freezer and stuff, you see density changes as you go from liquid water to ice water. So as you increase or decrease the temperature, the density of substances will change. So it is temperature dependent. If it was independent of temperature, then your density would never change, no matter how hot or cold the substance was. But that's not the case. Density can be treated also as a conversion factor. Okay, how? Well, depending on what substance you're talking about, you have a value that relates the mass of that substance to the volume. Okay, so we're going to look at how to use that in just a minute. Now, let's look at some illustrations for a second. I'm asking a question here, which is more dense? Let's pretend we have constant volume. Okay, I'm saying, I know the pictures don't accurately show us this, but say we have a liter of bricks and a liter of feathers, which is kind of bizarre to say. You don't think of it in terms of volume. But if you have the same volume, volume's constant, which one's more dense? Anybody want to shout it out?
The bricks.
The bricks. So if the bricks are more dense, what we're learning are the bricks obviously have a higher mass. Okay, 1 liter of bricks is going to weigh more, have more mass than a liter of feathers. So as mass increases, density increases. That's what we're trying to say. As mass increases, density increases. They're proportional, and that's because mass is the unit on top here. So as you increase density, you increase mass. Okay, now let me ask it a different way. Which one is least dense? Look at the units here. This is kg. G, kilogram or gram, it's a unit of mass. So we're assuming constant mass here. If you have constant mass, what do you notice about the size of the bags in each case? The bag of coins is the smallest. And this one, the bag of flour, is the largest. Okay. So which one is the least dense?
Flour.
The flour. Okay, so here what we can say is that as volume increases this way, volume is increasing, density decreases. Okay, so density and volume are inversely proportional. Density is inversely proportional to volume. All right. let's look at an example of how to use density as a conversion factor. So we're going to read this problem. Questions so far on what we just talked about? All right. It says you need 25 grams of rubbing alcohol. What volume? So what units are our answer going to have already? Grams or milliliters?
Milliliters.
Milliliters. What volume of rubbing alcohol should you retrieve if the density of rubbing alcohol is 0.7855 gram per ml at room temperature? So we're going to start with the mass that we're given, 25 grams. And what this density is telling us is that for every 0.7855 grams, I have 1 ml. That's what it tells us. The 1 is understood, per 1 ml. So just the same way as we would convert milliliters to liters or grams to kilograms, we're just going to convert grams to milliliters using density. So I want grams to cancel. I want my answer to have units of volume. So how do I need to write this relationship so that grams cancel? You can pretend this is over 1.
Grams on the bottom.
Yes, 0.7855 grams over 1 ml. Now it is a math problem. 25 divided by 0.7855. And you should get 31 point, I'm going to round, it's 0.8268, but I'm going to say 0.83. And our unit, so we need to cancel out the ones that we have on top and bottom, that's grams. And we have 31.83 milliliters. So that's the volume you would need to retrieve. So we just use density as a conversion factor to convert from grams to milliliters. Make sense? Questions on that? Okay, last one. This one's a little more complicated, and then we're going to spend the rest of our time working complex conversions. And here's the bet. We're not going to get through all these. So I will try to, for the complex conversion problems, post videos of any ones we don't get to in lecture today and make those available. But before you watch the video, practice it, try it, attempt it on your own, okay? We have several down here we'll get to, but if we don't get to some of them, I'll post videos of how to work them. Okay, the average density of blood is 0.00106 kilogram per cubic centimeter. If the average adult also has a volume of 5 liters of blood, what is the mass of blood in the average human body? So we know the volume of blood in the average human body is roughly 5 liters, but how much does that blood weigh? What's its mass? So notice it doesn't give you a particular unit here. It just says what's the mass. Well, the unit of mass in the density of blood that we're given is kilograms. So you're perfectly okay to leave your answer in unit of kilograms, okay? So if it ever doesn't specify like how many grams or how many kilograms or what it's looking for, just use the unit of mass that you're given. Now this density is very bizarre, right? It's kilogram per cubic centimeter. We are used to gram per ml. So there was a relationship Tuesday that I told you I wanted you to memorize. I said you can measure volumes 2 ways. You can measure volumes as either distances, cubic distances, or in units, in metric units of milliliters and liters and things like that. So anybody remember the relationship from cubic centimeters to milliliters?
One milliliter is 1 cubic centimeter.
Thank you, Allison. Okay, save the day. 1 milliliter equals 1 cubic centimeter. We have this in centimeters, but over here we have liters. So it would be best, and I know this doesn't jump off the page at you as this is what you should do, but it would be best if we get it all in the same kind of units, volumetric units versus cubic distances. So I'm going to take density and I'm going to convert it to milliliters so that we can use it properly. So instead of just writing cubic centimeters, it's a 1-to-1 relationship. It should be the same number, 0.00106 kilogram per milliliter. So we just substitute our units in there because all you do is multiply by 1 and divide by 1. So the number stays the same. All right, now we have it in kg per milliliter. So we need to cancel out milliliters, and we want mass in our answer. We want kg in our answer. We want units of kilograms on top, and we don't want those to cancel. So what I'm going to do is I'm going to write this number. I'm going to start with this number, and I'm going to put kg on top, and I'm just going to write it per 1 milliliter down here. So I just rewrote that as a fraction this time. Now I want to cancel out milliliters, and because I don't want milliliters in my answer. Well, what should I convert to? Well, we've got to use this value here. It's 5 liters of blood for 1 average human. That's some information that we're going to have to use. And in fact, you could write a relationship for that. It says the average adult, so 5 liters equals 1 average adult. The question here should be, well, what if you're above average? How many liters of blood? I'm just kidding. That's a dumb question. Jokes. So we're going to use that as well. But first, we're going to convert. To use this, we've got to be in units of liters. So let's convert from milliliters to liters. So what is our relationship? If we're going to convert from milliliters to liters, and I want milliliters to cancel, I need milliliters right there on top, and I need liters on bottom. Well, what's our relationship? For every 1 liter, there is 1,000, or you could write 10 to the 3 milliliters. All right, now we should see that milliliters cancels. Now we're in units of kilogram per liter, and now we can actually use this relationship because we want to know how many kilograms of blood are in an average adult. So we want kilograms on top per average adult on bottom. So we're going to use this last step. We want liters to cancel, so I'm going to plug in 5 liters here for 1 average. Oops, I misspelled that. So liters cancel. And now we are left with, here's the units we're going to have. Kilogram per average adult on bottom. And now we just do the math. So 0.00106 times 1,000 times 5. And I got 5.3, and it should be kg per average adult. So this was a 3-step problem. And you had to recognize this relationship from cubic distances to milliliters. You had to do that as well. Questions on that? There are different ways people choose to work these. The tip I like to do is I like to pick the number with the unit and put that unit where I want it. So for example, my answer wanted mass. Said, what's the mass? So I knew I wanted units of kilogram, and I wanted those in the numerator. So I picked the number that had units of kilograms, and I put that in the numerator to start my problem. And that way I ensure that I get the right unit in the proper place. Okay. All right, let's spend the rest of the time. I think we have like 5, 6, 7 minutes left doing complex conversion problems. So first off, a complex conversion problem, it involves like sometimes 5 or 6 steps. All right. So we've been used to just doing like simple 1-2 step conversion problems. We're going to get, and they're often in like the form of a word problem. So you'll read all these sentences, and you have to pick out what your relationships are and what the question's asking for. So here's some tips. We know it's going to require multiple steps, and you're going to have to be converting between multiple types of measurements. You're going to have multiple units. Number one, I encourage you to do all the conversions in one problem. Okay, see how we kind of kept it continuous here, and we didn't just like, literally people will do this on exams. It's a scavenger hunt for me. They'll take a problem like this, and they'll start up here, step number 1, and then step number 2 will be down here, and then I've got to come up here to find step number 3, and then the answer is all the way over here. I promise you I'll do that, okay? Don't do that. Just keep it as one continuous conversion problem. One, it's easier for you to follow what you've done, and it's way easier for me to grade. Write down all the conversion factors given before starting the problem. Okay, so we're going to do that. I'm going to show you what I mean by that. A good place to start is usually, note the word usually, not always, but usually with the first number or conversion factor given. But where I like to start is I look at what my question is asking for. For example, again, in this problem with density, it was asking for mass. The only units for mass I had was kilogram. So I'm going to find any conversion factor or relationship or number that has that unit that I want in my answer, and I'm going to start with that, and I'm going to put it on top, or if I need it on bottom, I'm going to put it on bottom, okay? And make sure you have, again, it's kind of what I just said, but your desired unit respectively on top and the desired one on bottom for your answer. All right, let's look at this first one. It says you get pulled over by a cop who's going to give you a ticket for going 0.28 kilometer per second in a 55 mile per hour speed zone. Where are you speeding? And we have this given conversion factor, 1.61 kilometer per 1 mile. Fun fact, my first year of college, I got like 2, maybe 3 speeding tickets my first year. Whoops, I haven't got one since, okay? All right, let's see. So we have, let's write out all the conversion factors given. So we have one right here in parentheses, and that is 1.61 km equals 1 mile. All right, another one that we have is right here. Anytime you see a slash or something per something, that's a relationship. So we have another one right here, 0.028 km equals 1 second, or you can write per second, doesn't matter. And we have another number here, but we actually don't use this in the problem. This is our standard. This is what we're going to compare to at the end. This is just our speed zone. Here's our actual speed, and then we're gonna convert it to miles per hour, and then we're going to compare it to 55. So we actually don't use 55 in the problem. We're just going to compare our answer to it in the end, okay? So these two relationships should get us where we need to go. So I want miles per hour. Right now I have kilometers per second. So I'm going to start, and remember it said usually, we're actually going to follow this tip right here. A good place to start is the first number conversion factor given. The first one given is the one I've circled. So let's start there, 0.028 km, and I'm going to write it over 1 second. That's how fast we're going. Now we need to convert kilometers to miles, okay, if we're going to make an accurate comparison. So we need a relationship. We actually are recognizing now we don't have all the conversion factors we need. We need another one. We need one that relates km to miles. So does anybody want to scroll up or have your slides handy, can find that relationship for us? How many, or anybody remember, I think earlier, was this correct? It was like 1.609, was that right, from earlier? We actually did a problem where we were, with the marathon problem. Was it 0.609?
Yes.
Confirm it, okay, thank you. So we're gonna use this relationship to convert from kilometers to miles. And then we also need to convert from seconds. We need to know how many hours is that. So if you don't want to go directly to hours, you could go seconds to minutes and minutes to hours. You can do that if you want. We happen to know 3,600 seconds in 1 hour. You could probably find that on a table, maybe somewhere previous in this lecture, or if you're just doing the homework, you could look it up. But on an exam, I would ask you not to look that up. So let's convert kilometers to miles. So we need kilometers to cancel, and we want to convert to miles. So I'm going to write 1.609 km on the bottom, and I'm going to put 1 mile on the top. And now we see that kilometers cancel.
I got a question.
Yes.
So we're using 1.609 kilometers to equal 1 mile, but in the question it has a given like 1.61 kilometers equals 1 mile. So why wouldn't we use that?
Oh yeah, that is a very good point. Thank you. I completely skipped over that. If you round here, it is 1.61. I'm sorry, I just missed that. I just got too deep and I don't know how I didn't see that. So yeah, we actually didn't need to write out we didn't need to write all this out. Oh, I didn't mean to erase it. I just meant to mark through it. Okay, we didn't have to write that all out. We actually had it right here. So if you round this 1.609, that is 1.61. Thank you very much. There we go. Simplifies things. Okay, so we've converted to miles. Now the other one we need to do is seconds to hours. So I want seconds to cancel on top. And now that we have seconds on top, we had it on bottom initially. Now we have the units on top as well, so we cancel that. And we're left with, the only things that don't cancel are miles on top per hour. Okay, and notice it is per 1 hour. So now we just do the math problem. 0.028 divided by 1.61 times 3,600. And we get 62.6 if you round 0.61. And the units are miles. I'm kind of crammed over here. Let me write it smaller. 62.61 miles on top per hour. Or you could write MPH. So we're going 62.61, roughly 63 miles an hour. We're in a 55 mile per hour speed zone. Yep, we're speeding. But here's the important question. How many of you think you could talk yourself out of that ticket? Officer, I'm only 12 over. Come on. I'm seeing some hands. That's great. Okay. It's 12:05, so we're technically at the end of lecture, and you can see there's 1, 2, 3 more that we didn't get to. These are all great ones to practice, but I'll post videos of how to work these as well. But please try them on your own first. I think you'll find that they challenge you in a good way. Real quick, while we are still 12:05 and not 12:06, today we learned 1, how to convert temperatures. 2, how to solve for specific heat or use the specific heat equation to solve for other variables in that equation. 3, we learned density and how to use it as a conversion factor. And then 4, we started doing complex conversions. That's what we did today. So those are kind of the big picture ideas that I want you to realize all this info falls into. Any questions? If not, thanks for joining. You're welcome to go, but I'll stick around for questions.
Roughly when do you think you'll have those videos posted for the complex conversions?
The ones in this lecture,
Mm-hmm.
I'm going to try to make videos for the dry lab stuff first.
Okay.
My goal is to do that today. Honestly, these videos should be pretty quick. I may not get all these complex conversions done by the end of the day, so for sure by Monday.
Okay. All right. Thank you.
You're welcome. Any other questions?
I emailed you about this earlier about my access code. I don't know if you saw it or not, but yeah, I still don't think it's letting me in. So
Really? Okay. Well, James, I'm gonna respond to your email after this, and I'll look at that. Okay, we'll get it
Okay.
taken care of. Thank you for reminding me.
Thank you.
I'll make a note of that. Any other questions? All right. Well, thank you guys for joining.